before you start each lab, make sure you've got the paperwork filled in, put in your first name, last name, student ID number, and again, make sure that you circle the appropriate lab section that you're in. Now, there's a number of questions here that it starts off with, and it says, what does IDE stand for? Name and explain the four major components of the CodeWarrior IDE. And all of this information can be found in Chapter 1, IDE, Integrated Development Environment. It talks about the four major components and so on. So you should be able to fill this in quite quickly before you even come into the lab. Now, what is the difference between platform target and build target? Platform target is a specific microcontroller you are connected to. Now, for those people taking DGS, you're going to find that when you do Quartus, you have to specify the specific device that you're connected to. So platform target is a specific, in our case, microcontroller that you are connected to. Build target has to do with compiler settings. And there's two extremes for the compiler settings. One is debug, and the other extreme is release. So debug, what it is you turn on all the debugging options you have and you turn off optimization. What is optimization? Optimization is making your code very efficient. So when you first start building your project, you use the debug and you turn on all the debugging because you want to make the program work. You don't care about it being efficient. The second type of build target is the release target, where you turn off the debugging and you turn on optimization, because in the release version you want to actually sell it and you want to make it as the most efficient you can to make sure that you're going to be able to outsell anybody else doing the same kind of programming. So that's what we have here. After watching the video, you should be able to figure out that this is the MC9S as in Sam 08 GB32. And we're going to pick it up at this point. We're going to switch over to take a look at running CodeWarrior to see all this happen and be able to fill this in as we go. When you come into the lab, what you should see somewhere on the main screen is this symbol for CodeWarrior, and you can double click on that. Now, for those people that have installed this, you should also be able to pin to taskbar here and just launch it by clicking here. Either way, you're going to launch CodeWarrior and you should see this screen coming up. Now, in the lab, what we have is we have a network setup, and you should never ever change where it puts it in here. Never change this. It should always be C:\CodeWarrior\workspace. Do not change this, or there's going to be some serious issues. It'll sort of kind of work, but then it really mess things up. So once you get to this screen, you're just going to hit OK, and CodeWarrior is going to load up, and then it's going to give us the default screen. So let me just back up here. So this is what we're going to have coming up here, and what we're going to do is we're going to create a new project. So what we're going to do is we're going to zoom up to the top here and under File, and make sure it says C/C++ CodeWarrior Development Studio. So we're going to go File, New, Bareboard Project. Now we have a number of options here. Let's just take a look at what our options are. First thing it's going to do is ask for a project name. So no matter what program you're going to create, it has to be part of a project. And we're going to call this Lab2. And notice here it's putting it in this workspace here. Now later we'll take a look and see how to actually move this off to a memory stick. So starting in Lab 3 or at least in Lab 4, make sure you have a memory stick ready to go. So it's going to put it in. Now remember, the C drive in the labs are not real drives. These are network drives that as soon as you log off, everything is gone. So if you want to save stuff in future, you will definitely need to have a memory stick. Now we're going to just go next. And out of all of this stuff here, we've got two possible things. We've got RS08, which has 4 families. We don't want that. We want the SO8. And out of all of these, we want the G family. So we're going to open this up, and this is the platform target, is this particular one here. The MC for Motorola Corporation 9S as in Sam 08 GB32. What we're creating is an application. And we're not creating a library. At some point, if you get really good at programming, you might consider doing that. But we're going to go next. And of these two choices here, this is the one you always have to leave, because this is going to be the BDM that we're going to have to disconnect and reconnect the USB connector to right at the start of the lab so we can talk to real hardware. But for home use, you can actually click on this and have one or the other available. So the P&E full chip simulation is for home use. This one here is for in the lab. Please make sure you get these straight, because on a lab test, if you're running the simulator and you have a problem, I will help you for 1 mark out of 10 to actually switch you from here to here. So make sure that in the lab you're always using this. So let's back up and we're going to go next, and here this is the only lab, or any time we're going to do this, we're actually going to work with absolute assembly. And we're not really going to program in absolute assembly, but I want you to see, because there's more details about how the environment is set up in this. Now notice this is what we're going to do after Lab 2. We're always going to go and just leave it at C. But for today, to get to absolute assembly, we have to uncheck this and check absolute assembly. And you'll see why shortly, that it's just going to give us a little bit more information than we need to help fill in things. Now whether you program it in C or assembly, we're not going to use rapid application development and a processor expert, because it's a very small micro. It only has 2K of RAM, so we don't really need a lot of help. We're really programming at a very basic level here. So as this thing comes up, it's going to create a project, and when we open this up, we're going to have sources, and this is main.asm. Now main.asm, ASM stands for Assembly Source Module. Assembly Source Module. And what this is here, it's called stationary, and what it is it's just dummy program that will work, but it doesn't really do much of anything. So we're not really going to concern ourselves with assembly language. What we're going to do though is take a look at some other things. So if we take a look here under project headers, we have 2 headers here, and this is the more important things that we're going to need for the lab. There's derivative.inc, which basically says use this guy, and MC9S08GB32.inc. This is like a header file but for assembly language. So if we double click on this, one of the things we see is memory map. Now in the memory map it says ROM start and ROM end. It tells the addresses where things begin and end, but there has been no ROM in modern microcontrollers except for 4-bit microcontrollers used for Christmas tree lights for years. When it says ROM start, ROM end, this really means flash memory. Now ROM start is a one-time burn. Flash memory, you can burn it as many times as you want, and that's why all the modern microcontrollers, if they're put into a product, you can then flash in a new version of the product, no problem. So ROM start, ROM end, these are just names that have been around for a while, but it really in our terms means for our microcontroller flash. And then we see ZRAM start, which is zero-based RAM start, so we can see that RAM starts at 80 and goes to 87F. So we have this kind of information available in the assembly portion, but not in the C portion. That's why we're sort of poking around here. So let's take a look and see how we can start writing up part of the lab. So as we saw when we ran CodeWarrior, this is MC Motorola Corporation 9S08GB32. Now Motorola is now known as Freescale, but these are things that were left over. ASM again is Assembly Source Module. Now when it says ROM start, it's really referring to flash memory, and what we need to understand here is where are things. Now notice flash starts at 0xC000, and flash actually goes all the way to here. Even though it showed that it sort of stopped a little before it got here, that's still flash memory, but the extra flash memory that goes up to FFF is basically for other purposes other than our own. So we only have access to a certain amount, but flash actually goes from C000 to FFFF. RAM goes from 0x80 to 0x087F, and there's an empty portion that goes from here, which is 0x880 to 0xBFFF, and I/O starts at address 0x0000 all the way up to 0x007F. Now when we fill these in, you're going to need to have this information to actually examine these types of memory in CodeWarrior. Later in the theory class, we're going to work out and show you how to fill this chart in and figure out the number of kilobytes to the nearest 1/8 of a K for these various address ranges. That will be done in the theory class. Now let's see, what is the exact platform target name? The reason we're asking it a number of times in here is so that you always remember it and can always do this without even thinking about it. And again, it's MC9S08GB32. BDM stands for Background Debug Mode. And the thing in the lab that we're connecting up to is a background debug mode pod or module. And when you go here, it says, can you write EEPROM and Flash an infinite number of times? Nothing in this universe is infinite. Even our sun is going to burn out in 500 million years, 500 million years. So nothing is infinite. So the answer here is no. Let's take a look then at answering some of these questions, 9A, B, and C, based on what we're working on in the lab. And we're going to be using something called a memory browser, as it mentions down here, to examine flash addresses, RAM addresses, and I/O addresses. That's what we're going to do next. Now this is pretty much where we left off from before. We had an ASM up here, and as I said, we just needed that just to get this information, where the memory map was and so forth, and we don't really need it anymore. And what we want to do is show you how we're going to set up for the rest of the semester just using C programming. So we're going to do, and show you a little bit as well as we do this, we're going to delete what we have here. And the thing is, what we want to do is do a complete delete. If we just say OK, it's going to remove it from the workspace, but it's not going to remove it from our hard drive. And we want to get rid of it completely. We haven't really spent any amount of time on it, so we're just going to do this, click. And if we don't check this and we just say OK, we cannot use Lab2 again as a project name. So let's do that. Let's get rid of it. And it's gone. And what we're going to do from now on is we're always going to create a C program. So we're going to say new bareboard project. And over here, when we slide over, we can still use Lab2 because we completely got rid of it from our workspace and also from our drive. So let's back up. So it's a little bit different, not much, but when we say next, again, what we're going to find is if we go up here, it's still going to be S08. We're going to go to GB, the G family, GB32, same as before. We're going to say next. And again, we're going to choose both this for home use and this for in the lab. And then we're going to say next. And from now on, we're just going to leave this default. We're not going to change it. We're not going to do anything more than just continue on and say next. Now at this point, again, we're not going to use processor expert, so we're going to say next. That's the same screen, but this is a little different. This is our C/C++ options. And what we're going to use here is the largest model possible, which is small. Instead of tiny, we'll use small. We're never going to use floating point, and we're going to use just minimum startup. This is the only thing that we're going to change. Now notice here it says minimum startup will just initialize a stack pointer, and that's it. It's the absolute bare minimum thing, and at this point we can just hit finish, and it will indeed create up here our project. And if we double click, here's our main.c. Now this again is default code. We'll talk about some of these things later, but right now we cannot go to the debugger, which we want to do, and even if we did this in assembly or in C, we can't go to the debugger unless we have binaries. And the way we create that in both cases is to say build project. Now we can either do build project this way, or we can use the hammer. As I say, let's get hammered, and if we get hammered, it's going to create up here binaries. Without that, we can't really get to using the debugger. So once we want the debugger, we click here and say debug as and CodeWarrior. Now sometimes it may not say CodeWarrior, so if you click here, if it doesn't, you click in main.c somewhere in that window, and you go down here debug as, and CodeWarrior will come up, and it's going to ask us which of these two options we want. Now this is great for home use, but in the lab we're going to choose this, and we're going to hit OK, and that's where we're going to continue on with the debugger. Let's see how that works. And it's loading everything in the target. This is the code here. If we look at main, this is that default main code that doesn't really basically do anything of any interest. Here's the actual assembly code, and as we saw before, we could actually bring up in here, here is the actual hex codes if you want. And what we're going to do is we want to take a look at the memory browser, and that's what we're going to be using today. We're going to be looking at that, and where do we find that? Well, let's take a look again up here at window. If we say window, and we can say show view. Now under show view we have a number of things, breakpoints and so on. On our debug screen right now we do not have the memory browser, and as we slide down here we can find it here. So let's click on that. And once we do that, let's back out again and see where it threw it. And if you take a look down here, by default sometimes it just throws it some random place on the screen. So what we're going to do is we're going to grab that, and what I want to do is put it on a different place of the screen. So I'm just going to hold down the leftmost button and I'm going to slide it up over here. Let's make it go on this part of the screen, on the second part. And we can make it go full screen or we can make it go part screen. It's just a matter of how you move the mouse. So I'm going to leave it over here. And then I can resize this a little bit just by sliding this over. So there's my original main.c. Here's the assembly code for that, and let's make this even, let's slide this over just a little bit more, and there's our memory browser. Now this is a new perspective, and if you remember we changed, or I had changed on the previous video, the debug to say debug new. And let's see how we can go and change that perspective. So again, if we go up here to window, and we can say window, and we can say save perspective as. And right now it's called debug because that's the default one. I'm going to say debug underscore new and say OK. And that's basically how you change the perspective to something that's a little better for what you want to do. Now for Lab 2, what we're going to do is we're going to be examining memory, and we're going to be using the memory browser. And as before, we can just double click on one of these and make it go full screen. And since we've changed our font size, if we do 0x 80, which is where our RAM is, if you look at the lab, you can see that it's showing everything that's physically on the board, but it's not showing it in the way that we want. And unfortunately, this current version of CodeWarrior doesn't allow us to change the default settings on up here, what's called the traditional layout. So what we're going to do is we're just going to right click here, and what we're going to do is we're going to make a couple changes. Cell size, we want to individually access each address, so we're going to say 1 byte. And the other thing we're going to do here is columns. Let's set our column size to 16. And the other thing we want to do is let's change our text not to ISO, International Standards Organization, but let's make it go to ASCII. So once we've got all that stuff done, let me just back out here a little bit. This is going to be our memory screen. Now this part of memory, if you can look at your lab, this is RAM addresses. Now RAM addresses, as you know, random access memory. So if I double click on this and I type in a 41, notice it's green, 42, 43, 44, and what you're going to find is as you're typing these things in, you can see them in hex over here and you can see them in ASCII over here. But it hasn't taken that, and it will not make any real changes until you hit the enter key, and doing the enter key, it's going to make it permanently changed. You've changed these values now by hitting the enter key, and notice they're now in red, which means it's made a change, and here it is again in ASCII. So one of the things we've learned is that our RAM addresses, you can see that these numbers aren't really anything special. They're just all over the place. Random access memory, when you first power it up, has random stuff in it, and when you change it, it does stick as long as the power is on, and this is typical of random access memory. Now again, this is RAM, so what we're going to do next is take a look at the next part of your lab, and what we're going to do is we're going to change this to now, we're going to go from RAM, which is 80 to 87F, we're going to go up to C000. And what that is our flash memory. Now let's just double click on memory browser, and let's zoom back out just a little bit here. And one of the things you're going to see as we look here is, let's just make this a little bigger and slide over here a bit. As we go up here a little bit, what you're going to find is that here's our code starting at C000, which is our startup for our code. We're going to see 450880. Over here we're going to see 450880. In other words, it's taking all the hex codes from the assembly language that we've got here and put them into memory for this default code that we've got. Now that we understand that, let's just double click on this again and take a look at this full screen. Let's go back over here. And so this is our default code. So anything in Flash that has not been burned in as code is FF, and that's what we can see on our screen here. So the real flash as FF because when it does any kind of programming of your flash, what it does first is it erases flash, which makes everything FF, and then it burns in zeros to form the 45, the 08, and so on. Now let's just double click on one of these FFs. It doesn't matter where it happens to be. Let's try changing that to 00. Notice it's green. When we hit enter, notice it turns it back to FF. Now this is typical of real flash. The real flash has a default of FF, and through the memory browser you cannot change that value. It will stay the same. Now let's take a look up here. If I double click on this and try changing the 45 code to 00 and hit enter, again it goes back to 45. So the memory browser allows you to change RAM, but it will not allow you to change what's been burned into flash. Let's take a look at the last part of memory, and the last part of memory we want to look at is address 0x0. Now you'll see here that this part here, this area in here is I/O. 80 to 87F down here is RAM, and then there's a big area of nothing, and then there's the flash. So here's what I want you to see. As I double click on this, which is address 1, if I happen to punch in a 90, now again it's green. When I hit enter, notice it comes back as 00. But if you take a look at what's happened on our 7-segment displays, you can see that there's a capital letter H there. So this is called a write-only register. And this write-only register allows us to send something and write something to our 7-segment display, but we read back always a 0. Now we can also, this is our left 7-segment display, this is the next 7-segment display, so this is address 1, 2, this is address 5, which is the next, and 6. So we can actually change our 7-segment displays by pumping values in here. So that's by putting in a 90, we can do that. If I put in, I don't know, a 55 and hit enter, you can see it's changing again. But every time we put in a value, let's go back and change this back to 90 because that's part of our lab. What we want to do is put up the message help. And the help message that we're going to put up is going to be based on you being able to figure out what is the pattern for an E and putting it into address 2. And in address 5, we're going to put the 2-digit hex number that makes an L and an P here, and that's one of the first initials in your lab that you're going to have. Okay, by putting something into address 1, 2, 3, 4, 5, and 6, we can change our 4 7-segment displays. This is address 6, 789A. If we go to address A and double click on here, and if I happen to put in AA, if we watch on our red LEDs, we can see that the pattern is on the lower LEDs. Now if we go up here, which is address 9, so this is address A, go back to address 9, if we put FF, what it's going to give us when we hit enter is 03, and you'll notice that the left two red LEDs just came on because this address, address 9, only has 2 LEDs. So the only values you can put in here are 0, let's try 0, whoops, sorry, let's do that again, 0, and you can see those are off. We can put in a 1, whoops, 01, better do this right, or we can put in a 02, but every time we type in these numbers, notice that it remembers these because these are read-write registers. So we can put in only values 0, 1, 2, or 3 in here, and so these addresses, or 9 and A rather, control the red LEDs. That's A, B, C, D. This address here, if I put EE, this is when we hit the enter key, you'll see the green LEDs will turn on in that pattern. So this is how we actually, right at the hardware level, deal with I/O devices. We put a number into an address. If it's a read-write address, it keeps that value and reads it back, whatever you wrote. But if you have a write-only register, as we have here for 1, 2, 5, and 6, you put a number in, it goes, but it then reads back as 0. So this is kind of, I/O is a little strange in that way. If you have a read-write register, it's very easy to sort of see what you put in, but when you use a write-only register as on the 7-segment displays, you don't get that. Now we also have a couple of other things here, and these have to deal with our switches, our inputs. So far we talked about output devices. We've got 4 7-segment displays. We've got 10 red LEDs. We've got 8 here green LEDs. And then we want to start dealing with our switches. And we're going to take a look at that next. Okay, now what we're going to see for these two is that there's two addresses here, address 11, hex, address 12. The lower two bits here of this address are the upper two switches. The other 8 switches form this address, which is address 12. So how do we change that? We can't change them just by pumping numbers in. What we're going to have to do is actually change the physical device. So if we look here, this is 1, 1, 1, 1 for these lower 4 and 0, 0, 0. That's why we're getting F0. What I'm going to do is change this to 1, 0, 1, 0, 1, 0, 1, 0. Now, nothing has changed on our screen here, but if I double click on this number here and I pump in 0, 0 and hit enter, you can see that it's now changed to AA, which is exactly what the switches are reading. So how do we change the upper two switches? Well, let's put them both on. And what that should mean is before it was a 0, 1, now it's a 1, 1. So what we should see now is this number changing to a 3, an E3. So let's just double click on here and punch in 0, 0, and indeed what we're going to see is E3. And you may be wondering, why are we getting E3? Well, what you're going to find is these 3 push buttons here form the upper 3 bits of this address here, address 11. So right now, if you don't push these push buttons, they're 1, 1, 1, and then there's some no connects, and then these things here. So that's why you're always going to find 1, 1, 1, and then whatever this is the lower 2 bits. And that's basically how our devices work on our microcontroller. The input, you have to put a 0, 0 in to make it force it to read back the actual value, and for the other ones you just put the number in and it changes the actual device. So let's just take a look at the simulator, because part of Lab 2 asks you how is the simulator different than the real deal. So what we're going to do now is when we go over here, let's go to my debug new here and take a look and see how things work. So let's take our look at our memory browser, because we still have just garbage code over here. We don't have anything real to look at. It's just the basic skeleton code. Let's take a look at our memory browser and let's see how things are different. First, let's take a look at flash memory. And again, let's right mouse click, change our cell size to 1 byte, right mouse click, change our columns to say 16. Well, it's 32 actually, columns 32. And let's go back here and also change our text to ASCII. So as we go through here, remember what we saw before. We saw up here all these same codes. This is our default code that comes up as part of that skeleton C program. But notice we've got 0 zeros here. That's kind of bizarre. This is not real flash. So what is the default? The default for simulated flash tends to be 0, 0. If we push in an FF here, remember when it's green it hasn't changed until we hit the enter key. Look at that, it allows us to change what it thinks is simulated flash. Also, if we take a look up here and we change this to say 0, 0 or something different, notice it takes. So there's a big difference, as you'll see, between real flash and simulated flash. And it asks you what is the difference, and basically the difference is that in real flash it's a default of FF and you cannot change it with the memory browser. Now this is on page 4. In simulated flash the default tends to be 0, 0 and you can change it to any value you like. Starting address for absolute assembly programs get downloaded into C00, as do C programs. And as we saw before, one of the things, let's take a look at RAM. Now RAM starts at 0x80 and everything from here to 87F is RAM. Now most of the stuff, it's more convenient to probably put things in at address 100. As you'll see in the next lab, we're going to be putting things in there. But the important thing is that RAM itself, simulated RAM, it has all zeros. Isn't this interesting? But we saw in the real version of RAM, there was random values in some of these addresses. Now, one of the things you're going to find is that if we take a look and we declare a variable, our variable is actually going to go near the top of this. So let's take a look at 850. And what we're going to see is that at 87F, this is the top of our stack. Let's just slide down here a little bit. All of this stuff from here to here is called the system stack. We're going to look at that later, and this is where it's going to put our variables. And if we declare a variable to be char, it's only going to use 1 byte. If we declare a variable to be integer, it's going to make it 2 bytes. If we declare a variable to be long, it's going to make it 4 bytes. Now RAM, as we said, starts off with random information inside here, and what you want to do is, if you're declaring a variable, that's fine, but it does not put a default value in there for you. So one of the things you have to do is initialize the variable, whether it's char, integer, or long, because if you don't, you're going to have a random value there, and it's going to make your program do weird and wonderful things. So this is pretty much everything that we need to know now to finish off lab number 2.